It's great to be here, and I wanted to talk about what happens when companies really try to deploy these algorithms in the real world. I've been running CrowdFlower since 2008, actually, so I've been doing this long before AI was cool, and I've gotten to watch thousands of our customers, from banks to startups, try to deploy machine learning algorithms and succeed and fail. And it's obvious that these companies have tons of business processes that are totally applicable to machine learning. And by this point, they have the in-house teams that can build RNNs and CNNs and LSTMs. They can make the algorithms work, but they really struggle to get them deployed into production. So I want to talk about some of the non-algorithm issues that come up when they try to do this. So the first big issue is that machine learning projects are incredibly unpredictable. And this is maddening if you're used to engineering projects, which are already fairly unpredictable. Machine learning is 1,000 times worse. And I think the best example is from this movie 2001 Space Odyssey. How many of you guys remember the chess scene in this, when he plays chess? So apparently, in this chess scene, the computer plays chess with the astronaut and kind of talks a little smack in a natural-sounding way. And they wanted to remove the chess scene because they thought the audience would think it's unrealistic that a computer could beat an astronaut at chess. But nobody realized that the truly amazing thing that we do as humans is talk shit to each other. Who would have thought that would be the real challenge that we still haven't even come close to solving? And so how does this apply to concrete problems? Well, has anyone used Kaggle? Anybody know about Kaggle? Kaggle is an amazing company that was actually backed by Bloomberg Beta and sold to Google. But I used it, and what you can do is crowdsource your machine learning tasks. So I took one of our customers' problems, search relevance, common problem, and I posted it online to get people around the world to work on modeling my e-commerce search data. And in the first couple days, it was incredible. I went from under 35% baseline, and the first day someone beat the baseline. And then the next couple days, tens of people logged on, and they actually solved my problem for me. And I saw this accuracy going up from maybe 34% to 65%. And I was really wondering how good this was going to get. Would I get to 95%, 99% accuracy? And actually what happened was it completely flatlined. We only got maybe 2 or 3% more improvement. And you might say, well, maybe this competition was boring. Maybe the people that entered in the beginning were the only people that tried it. But actually, this competition had a lot of enthusiasm. We had thousands of people participating, going back and forth, improving the algorithm. They were just getting tiny, tiny improvements over each other. Just these 0.1% improvements that were exciting for them, but really weren't useful to our customers. So when I see a graph like this graph of Google self-driving car performance, where it starts to look exponential, and everyone talks about these exponential curves, I wonder, are we going to have self-driving cars the next year, or could this flatline in ways that we don't expect? Because they really do. So what do you do with this? What do you do with these projects where you're not sure if you're going to get stuck at 80% or if you'll blow through that number? A really simple thing to do is something we call human-in-the-loop, which is so easy to understand, and so many companies really do it. I want you guys to all know about this. You take your AI classifier, and where it's confident, you use its results. So if it's 80% accurate, 80% of the time, it might be very confident in the results. And if you take only those 80% of the results that it has, you can actually get very high-quality results. You take the results where it's not confident, and you send it to a human to label those. And so you get a reliable system. And I think the best example of this is the post office, which deployed OCR in 1982. And you can imagine that system had errors. In fact, they only used it 20% of the time because it wasn't a very reliable system. But actually, even now, they use humans for some of the handwriting recognition. So if they had waited for the system to be perfect and accurate enough that they could replace all the humans at once, they would have been at least 35 years late to deploy OCR. So they were able to get the benefit right away. And here's just a real-world case study with a customer that really cared about accuracy because they're routing support tickets. They don't want to route them wrong. And their NLP experts made them an 80% accurate model, and they said, great, I can't use that. But it turned out 40% of the time, the algorithm is 99% accurate, and so they were able to get 40% cost savings instead of deploying an unreliable algorithm. And then, guys, if you're on your laptops, this is the most amazing, world-changing use case of AI. This is Coca-Cola, and you can actually take a picture now of your bottle cap. And they use CNNs to actually read the label to decide if you want a prize. But it's pictures taken by human beings. So even this problem, not completely solved to their satisfaction. So they actually make a website where they show you what they think the letters were on your bottle cap, and you can go in and edit the letters where it has low confidence, and it highlights those points. I know, mind blown, right? Yeah. So here's the next problem. Important challenge. Training data is required. I mean, now everyone knows about training data. 2 years ago, people didn't realize this. A lot of people outside the room, they don't know that training data is required. And it's so required. It's required more than you ever could possibly imagine, right? So this is these graphs that made me want to start CrowdFlower. This is what I was thinking about back in 2008. You take 3 algorithms, now they all seem old, but they all have about the same accuracy level, right? So it goes from 18% error rate to 17% error rate. And you can really publish a paper on that. But you can't deploy something based on that. 18% error rate, can't use it. 60% error rate, still can't use it. So what do companies do? My first job, I did a lot of feature selection. Now we do other things involved in sort of framing our problem and making our problem work for algorithms that are really outside of the algorithm. And these things really matter, but they're really, really hard to manage, right? This is when you do a Kaggle competition, this is what the people are really doing inside of that competition. The problem is you don't know which features are going to give you that breakthrough. But one thing almost always helps, everyone forgets to do it, and that's just add more training data. And often you really can add more training data. So in this case, I took a task that I had, document classification, and I just doubled my training data, and the error rate improvement was similar to doing the best possible feature selection, and then I double the size of my training data again, and actually get that same improvement. There's actually one more thing that I can't find any paper on, but every company, every person that's really worked on machine learning knows this really matters. This is so simple. Clean up your data. So actually, just cleaning the data got the same benefit as doubling the size of my data and then doubling the size of my data again, right? So whenever I talk to people actually working on machine learning, I say, if you can, sometimes you can't, but if you can, the best thing you can do is clean up the input data into your algorithms. And so everyone remarks on this, but it's actually really rational. Data scientists spend all their time cleaning data, right? The good ones do, because that's what they should be doing to make their algorithms work well. And it's kind of remarkable that we hire these expensive teams and put them to work on doing something they weren't actually trained to do. I never took a class on cleaning data when I was in school, but I've done a lot of it in my life. I'm not the only person to observe this. Actually, Peter Norvig at Google wrote a really excellent paper about this maybe 12 or 13 years ago, where he basically noted that the cases where machine learning succeeds is not where problems are easy or where problems are hard, but they're cases where there happens to be lots of training data available. So for example, in translation, there's lots of data available, or speech recognition. These are really, really hard challenges, but we actually create training data as a byproduct of the stuff that we do. And there's a great paper here where a bunch of researchers at Microsoft, and this is 10 years ago, they show that basically every time you increase the order of magnitude of the data size of the size of your training set, you increase the accuracy of the algorithm. And it sort of looks like it might be flattening out here. I actually kind of wonder when you look at this graph, right? Is it actually, does it still matter? Does it matter at scales of like 1 million and 100 million and 1 billion that we're used to working with now? And actually, Google came out with a really interesting paper this year called The Unreasonable Effectiveness of Data Revisited, where they take their image algorithms and they scale it up to 10 million, 30 million, 100 million. I mean, this is like 6 or 7 orders of magnitude bigger than the data sets that I was used to when I was studying this stuff. But the accuracy improvements seem to still keep coming at every order of magnitude that we see. And so training data can be really difficult and expensive to collect. So this is an example of people using my company's product to label literally every single pixel in an image with, is that pixel a tree? Is that pixel a road? You can imagine that self-driving car companies need to do this constantly to make their algorithms work. But you can be smart about it, and in fact there's this benefit, this extra benefit of the human-in-the-loop design pattern that I was talking about, which is that when you take your confident results and use them, and you take your non-confident results and send them to a human annotator, you're actually creating the perfect training set to improve your algorithms over time. This is the best possible design pattern because the efficiency of your system will increase over time naturally just by doing it. So when we see companies successfully deploy things, they always use this design pattern. They always keep retraining their models and improving them continuously. And in this case, with this customer support ticket, we see the same thing, where you see that arrow in the bottom, right, where they feed back in the 60% handled by human reviewers, and they've gotten that number down to 20 or 30% handled by human reviewers. And even in this amazing bottle cap example, you'll notice an arrow in the lower right, where they're actually taking the data and feeding it back into their algorithm to make their bottle cap algorithm continuously improve. So there's one more thing, which I think there's not such a clean answer to, but I think is super, super important, which is that these algorithms are incredibly painful to deploy. And I've been thinking a lot about that lately. Why is it so hard, once you even have a working algorithm, to get it to actually run into production? And I think the difference is just in looking at this code. So, I wrote the code on the left here, and this is like normal human-readable code. This is what we've been writing for the last 50 years. And then I generated the code on the right. And so there's some obvious differences when you look at the two, right? I mean, one difference that you can't see here is that the code on the left is maybe 1,000 lines or 100,000 lines or 1,000,000 lines at most. The code on the right is gigabytes, and it gets bigger every time NVIDIA releases a new graphics card. Right? So now the code that we deploy is gigabytes of data. It'll be terabytes soon, and it's completely inscrutable. Right? The code on the left, if I change something, if I want to improve it in some way and I tweak it, I get a meaningful diff of what I did, and someone can go back and look at that. If I put this in a car and it crashes, I can walk through where the code crashed. But if you look at the code on the right, it's completely inscrutable. When I make a new version of the code on the left, I actually can look in GitHub and see what changed. The code on the right, if I had one new piece of training data, every single number in that crazy file changes completely. And then finally, we spent 50 years kind of learning how to debug the code on the left, and I think we have really no idea how to apply that and how to debug the code on the right. So I think we need a completely new set of tools to handle this new kind of code that we're creating, and I don't have a good, clean answer to that problem yet, but I'm thinking about it a lot. And I think it's worth it to think about it because sometimes when you see this exponential curve, it blows past human accuracy and it just keeps going. Right? So you can see that the new AlphaGo release is as better as the one that beat the human grandmaster as that one was than the one that better than Crazy Stone, which is a really strong human amateur. Right? So when you deploy these things, it's worth it because they often keep improving. So thank you very much. It's great to talk to you.